All right, so we're live now. Okay, so the next thing that we need to do is find the confidence interval for the standard deviation. So that is right here. Confidence interval for the standard deviation. So we're going to stick with our information that we have right here. But we're going to say I want to find the confidence interval for the standard deviation. So I want to figure out how much variability or how much variation is actually at these schools. So I'm going to use this formula right here. But I need to understand what, well, first of all, I understand that N is the sample size. S is the sample standard deviation, which we already have. Then I need to know these values for chi-squared, which come from table G. And as we did from last time, to find the value for what is on the right, that's alpha divided by 2. So I have alpha, 0.05. I have alpha divided by 2 is 0.025. Degrees of freedom is 27. So the value to the right is 0.025. So I'm going to go to my chi-squared table. I'm going to look under that column. I'm going to look at 27 degrees of freedom. I'm going to get a number. Now, there's something that happens here. If I know how to do this problem and I do it for you, well, that's positive. You need to know how to do the problem.
Can you go a little slower, just where you got those numbers from?
Okay, this I just came up with. I just created these numbers.
Right.
Okay, this I tell you, 95%. Alpha is 0.05. How do I know it's 0.05? How do I know that this is divided by 2? Because I took that divided by 2. How do I know what this is? 27, because it's 28 schools. Track 1, 27. We need degrees of freedom, yeah. All right? Okay. Right now, we're looking for chi-squared to the right. And that's going to be alpha over 2, which is 0.025. So I'm looking at 0.025 with 27 degrees of freedom. It's 43.194. Where do I look for what is up to the left? It's 1 minus alpha over 2. So in this situation, I would take 1 minus 0.025. What's that number? .975. Where am I looking? Table G. What column am I looking at? 0.975. How far down do I go? 27 degrees of freedom. What number do I see when I get there? 14.573. Okay, so if you're looking at table G and you go over to column 0.975 and you go down to number 27 for degrees of freedom, you see that number right there. That goes into our formula. I'll give you 2 minutes. See if you can make this happen.
You can just It's a weird difference. Yeah, for a 10.5, right? Yeah. Just making sure it hit. Yeah.
All right, Ellie Cooper, what do you got?
16.05 and 27.46.
Ooh.
I think I might have typed in a number wrong.
Did we get 43.194? Is that really what it says?
Okay, now I got it. No. 27.6. Yeah.
That's what it says, 43.194 or 40. Yeah. Huh. Well, that's kind of weird. Because when I do it on the computer, it says 43.195.
I still with that on the last problem. Yeah,
Yeah,
I was putting
so.
left in Excel and Blackboard right out there. Oh, no.
Okay. So I've got 16.05 and 27.63. Okay. 27.63. Yes.
I know. Right.
Like in the last problem and this problem, what do those numbers represent?
Okay, in every situation, in confidence interval, they represent the interval for the measurement of the population. The sample number was 20.3. These numbers represent where the actual population number is. So if I ask the question, what's the standard deviation for the number of students in extracurricular things? 16-year-olds. The standard deviation for the sample was 20.3, but that does not represent all the schools. I just took a sample of 28. So if I say, what's the actual standard deviation for all the schools? It's somewhere between 16 and 28. Okay, so I got the number 20, but that's not the answer for all the schools. That's just the answer for the sample. If I say, what would be the standard deviation for all the schools? Somewhere between 16 and 20. Right to this. Okay. Any other questions about this right now so far?
So this last problem problem, like, and the form of a word problem will be laid out the same as the previous one? But that's what I get confused with when they actually put it into a word problem.
Yeah, well, I don't have to tell you the mean in order for you to do this problem.
So like, how would this look in a word problem?
That's not an issue too, in a word.
Because like, we have a word problem for the last two, and I'm just confused how I know.
All right, so if I take a look at this last problem here, problem number 9, okay? It gives me a list of numbers, and it says estimate the population variance and standard deviation for this thing with this amount of confidence. Okay? And then it tells you how much they want you to round off. Okay? How do I know that this is a problem doing confidence interval for standard deviation? Okay, it says estimate something with a certain amount of confidence. When you're estimating with an amount of confidence, that's a confidence interval problem. Okay? What I will put on the test, more than likely, will look like this. I want the 95% confidence interval for the standard deviation for this data. Okay. Probably not. Probably not. Okay. All right. Any other questions about these confidence interval problems? Okay. If I were to ask you the question, how important is the confidence interval, what would you say? Actually, when we talk about the confidence interval, there are people in statistics who say that the confidence interval is the only way to do statistics. Question. There are some people, especially recently, within the past 5 or 10 years, who have said that we should only use confidence intervals to describe anything in statistics, because confidence intervals are telling us what to expect from a population. If we want to make any decisions, we should make our decisions based on what the confidence interval tells us. For example, if I want to say, hey, who's gonna vote for a politician? And then I say, okay, I want to know how many people are going to vote for the politician. If I say it in terms of a confidence interval, it's somewhere between these two numbers. Then that tells everybody how accurate my numbers are, how good my statistics are, or whatever else. So I should not say 40%. I should say between 37 and 43%. And then everybody knows how well they can trust my numbers. So there are people who say everything we do in statistics should be done using confidence intervals, because that's actually communicating the reality of the situation, how much we don't know and how much we do know about a thing. Okay? Confidence intervals are very important. Some people say they're the only thing we should ever use in statistics. However, for about 100 years, they're not the thing that we used. We used something else. Okay? And the something else that we used is called hypothesis testing. So if you have some kind of a research article that somebody does for a specific thing, and believe me, there's plenty of them out there, right? You talk about care of senior citizens, the impact of law enforcement, nutritional questions, anything really that's out there in terms of research. Most of the time, they use this thing called hypothesis testing in order to try to figure out what's going on. So it's pretty important for you to know how this works, to know how that process goes. Okay? Now, this is not easy. What you will find is that there are 6 different steps for each problem that you do. And those steps are all connected to each other. And so then you have to know how that works. Now, on your formula and information sheet, which is on Blackboard as well as various other places, it has something called a procedure table. And this procedure table is going to show you how to do the process of hypothesis testing. Okay? You will be given these procedures. You don't have to write them down right now. In fact, I'd prefer that you not. But I want you to see what's going on here. These are the things that you're going to need to do. This will be given to you on the test. Okay? Once you get to the end of a problem, if we go to resources here, notes, make sure I've got this on here. Well, I'll have to put it on there. When you get to the end of a problem, then there will be 7 different things that you will need to say about the situation. I will tell you what those 7 things are, and you will be able to write those down as well, okay? I thought I had it posted here, but I don't know where it is. So I'll get that. Now, in order to make this happen, I created 3 videos, which are in the notes section, and that's what we're going to do right now. I'm going to click on these videos, and we're going to watch them, and this is how I explain hypothesis testing.
Should we take notes or just watch
It wouldn't hurt to take notes, I suppose. I do have notes up here on hypothesis testing. So it's out there on Blackboard as well. And you can certainly watch the videos over and over again, whatever you want. Okay. But here we go. Part 1. Volume. Nothing's happening. Oh, no wonder. Okay. Back that up, 100%. Make this.
All right. So the question that we're talking about in hypothesis testing is how are we going to make some decisions? Consider this idea. Do students at Western own cats more than the national proportion? So we're talking about how many cats do people normally own? And surveys out there say about 30%. And so I want to know, what about students at Western? Do they own more cats than that? So then how am I going to prove it? Well, I have a problem, okay, if I'm going to try to prove that, because I know that samples are not accurate, right? So that if I take a sample and I say, well, I did a survey and I found out that it was 40%. Well, that doesn't prove anything. It doesn't prove that it's different because it's a sample, right? Because we've talked about sampling variation. Sampling variation tells us we cannot prove anything directly by just looking at the samples. But what we can do is we can think about that sampling variation because we know that sampling variation has a distribution, right? And we know that if our sample size is large enough, the sampling distribution is going to be bell-shaped. And so then we can control, or we can understand what might happen, because when we do samples, we can know how much variation is going to be in our samples. So then we can actually figure out what to expect from a sample. Now, what the logic of hypothesis testing goes like this. If we get an unusual result, that means that then our assumption about population may be wrong.
Wrong, that's the word, wrong.
So I'm looking at my sample. I say, all right, I've got variation in my sample, and I can expect that, right? But if something happens which is unusual, then maybe there's something going on with my assumption. Remember, when we talked about this, we assume that the population and the sample distribution have the same mean, okay? But if we get some kind of an unusual result, it's like, wait a minute, that may not be right. Let me give you an example here. Consider that this idea, do students own cats more than national proportion? The national proportion is about 30%. So if I say that the national proportion is 30%, and yet I get a sample which is out here at 40%, then I look at that and I say, well, wait a minute. If there's a large, significant difference here between these, then that means the meaning of that measurement, it could be that what I'm measuring is not actually from that population. That with Western students, when I took that sample, they don't have a proportion of 30% cat ownership. And so that is why my sample was so high at 40%. So what I'm looking for is unusual results, which will then tell me that where I got my sample is not the same as the assumption that I made. Okay, I'll come back to that in just a minute. But that is the basics of hypothesis testing.
All right, so I'm going to show you a picture of what I was talking about. If I know that P is equal to 30%. If I were to know that a population has 30% cat ownership, then my P hat will fluctuate, right? But here in the middle, 0.30, that's kind of where I would expect it to be. Well, what if it's a lot higher? Let's say that I asked everybody in class how many people own cats, and it was 90%. Then I would say, I don't think that's just a random fluctuation. I think there's something going on to cause this number to be very different from me. It's not just a random chance to have this much difference of 90% versus 30%. Because remember, this is like Plinko. It comes down here. Sometimes it's higher, sometimes it's lower. If it's way out here, that would be an unusual result. And I would say, it's not just a random fluctuation. There's something going on. This happens to be a cat-loving class or whatever. Okay? If it was this high. But what if it's just 40%? Is that just a random fluctuation? Or is it actually true that there's something going on with this class that makes it different from the 30? So I need some way to measure how different one number is from another. Is this sample number out here, could it come from a population where it was 0.30? Or would that be unusual? So I have to have some way of figuring that out. So that's what hypothesis testing does. It's asking the question, is something unusually different? Or could it just be a random fluctuation of a sample? That's what we're trying to decide. Okay, so that was number 1. Now we're going to go do number 2. Different microphone, so it'll be a bit louder here.
Can you repeat what you just said?
Is something unusually different or something?
Just a random fluctuation. Sure. Okay.
Talk about hypothesis testing, what it is. Now we're going to get into the nitty-gritty details. So in order to make this work, we have some traditional views.
Okay, I'm going to turn this up a little bit. Fortunately, I have this little thing that turns stuff up. So let's back that out.
All right, so we talked about hypothesis
Whoa,
testing.
a little much.
What it is. Now we're going to get into the nitty-gritty details. So in order to make this work, we have some traditional views, traditional ideas of what hypothesis testing is all about. And so we start with describing our basic assumption, which is the null hypothesis. The null hypothesis is our standard. We set a standard and we say, assume this to be true. So the null hypothesis is going to have an equal sign in it. And so it's an H with a subscript 0. Null hypothesis, which is saying to us, this is our assumption. It can be either about mean, or about a proportion, or about a standard deviation, right? Those are the three things we've been working with here. And then we have the question of what is it that we're trying to prove? Very important to understand. What we're trying to prove is called an alternative hypothesis. We cannot prove the null hypothesis. We cannot ever prove from a sample that we have something equal to a number, right? Like we said, you can't do that. A sample is not accurate, so you cannot prove equality. But what we can do, this is the power of hypothesis testing, is that we can prove a difference. We can say, with a certain amount of confidence, the population measurement is either greater than or less than the number, some kind of standard number that's been set for us. Now, it's generally, when we're talking about these things, we're talking about alternative hypothesis as being different from the null hypothesis. Then that means we're looking at the tails. If we're looking for the sample as being higher than a certain number, that would be a right tail. If it's lower than a certain number, that would be a left tail. And it is possible sometimes, if we don't know what we're doing as far as either less than or greater than, we'll say it's two-tailed. It's a two-tailed test. I don't like two-tailed tests. I'm strange compared to other teachers, maybe, but I just don't like it. Because if we have the sample information, then we know something about what direction we're going. So what I give you will be one-tailed tests. Now, of course, when we say we're going to do a test, then we can adjust how confident we want to be in it, just like with confidence intervals. So we can say, all right, I'm going to pick alpha. My chance of being wrong, and most of the time it's 5%, 0.05. But we pick that, right? And so then we have the tail. If you have the distribution, and then you have the tail, and it's got an alpha in it. That place out there, that's called the rejection region, or the critical region. Okay?
Okay, I'm going to put this picture up here so you can see. If I have something that's right-tailed, that means, for example, I would have something where I'm trying to prove that my group has a higher number than what I expected. That would mean I have a right-tailed test. I would be looking at this to be alpha. The area right in here would be alpha. And so then this place here, from this point out, this is called the rejection region. And this dot right here is something that we call the critical value. Again, alpha is my chance of being wrong. It's going to be a small number. A lot of times it's going to be 0.05. And then I want to know what is the number that separates out that tail. That's the critical value. The critical value is that place that separates so that everything greater than that would be in this alpha region. That's called the rejection region out there. Now, what would left-tailed look like? Well, certainly, seem reasonable. Left-tailed, like that. Here is my critical value, and this would be my rejection region. And how would I know that it was left-tailed? My null hypothesis always has an equal sign. The alternative would be a less than. Now, it is possible, and your textbook will do this. It will have what's called a two-tailed test. But I'm not going to give you those, all right? Not till later, at least. If it's two-tailed, then that would look like a confidence interval. It would have alpha divided by 2. They would have a left and a right. These are not. These are one-tailed tests. And this is on the bottom of table F, the T-score table. It shows you the difference between the one-tailed and the two-tailed. Okay. But remember, it is possible to also go to the left or to the right. Either one is a possibility here. Okay.
Okay, so this is what we're saying, is that if the sample comes out to be in that place out there, in that tail, then we've found the place. We've found the difference. It is significantly different if it's out there in the tail, if it's in that rejection region. And so then that's how we set this up. We're going to set up the hypotheses. We're going to be trying to prove the alternative. We're going to be looking for where the tail is. And then we're going to use some kind of a equation or formula to say, all right, is it out there? Is it in that tail? And then once we get it out there, if it's out there, then we say we reject the null hypothesis. That's the goal. We want to reject the null hypothesis because that means we've proven something. We prove that there's a difference. Well then, okay, this is where a lot of people have trouble, all right? If you Do not reject the null hypothesis. You have not proven anything. So we have two alternative choices when we get down to the end. Either we reject the null hypothesis or we do not make a decision. We can never prove that equal sign. We can never prove that something is the same as a certain standard. So either we prove it's different, we reject the null hypothesis, or no decision. Those are the two possible options. So I'll come back and talk about more. But that is the idea of the main steps for hypothesis testing.
All right. So, once again, when we do this, we're trying to figure out if things are unusually different. And this is the language that we use. Is it out in the rejection region? Is it beyond the critical value, either to the right or to the left? If it's out there, then there's a significant difference. If it's not out there, then we don't know if there's a difference or not. Can't tell. It could just be a fluctuation. All right, so on to number 3. A different microphone, and I think I had a cold, so anyway.
Talking about hypothesis testing. There's some more details that I still haven't fully gotten out there for you. And I'm going to actually go through the example of the cabinet chip and show you exactly how this really works. Now, there are these specific steps. This is listed on your laminated sheets, as well as in the textbook. These 5 steps of how hypothesis testing actually works. We'll go through them in detail. There's a couple of new things here. The idea of the critical value in the test we're making. But first of all, here's the question. Here we have this survey. Do you have a cat in your household? So we have 40 out of 100 that say yes. Of course, that's 40%. Now we want to say, is this actually higher than the national survey of 30%? Household at the table in the front. So, as we talked about in the earlier ones, we've got the null hypothesis. That's the standard we're setting. The 30% is the standard. And then we want to prove that what we've got for the students that we surveyed is that they're not part of that population. They have a greater value. Now, what is the critical value? Well, it's the number which tells us where alpha lives. Okay? If we're looking for alpha 0.05, then we can look that up on the table and find that that means the critical value is 1.645. Anything greater than that would be an unusual result. So we're going to compare then this critical value, that's where alpha is, and we're going to compare it with the test value. Test value information is going to come from the sample and also from the statement of the problem. And we're going to get a number that we're going to use. This is how it works. What is the test value? There's a formula on your sheet. The z-score that we need when we're doing proportions, we take p hat minus p over square root of pq over n. Numbers are listed there for you. We come out with 2.182. So now we can make our decision. If we have this thing in the rejection region, then we're good. We proved it. And that's what happened here. The test value comes out to be 2.182. The critical value is the 1.645. So we're out there. We've done it. Now we want to summarize the results. The long form has all the details about how this works. But then we just want to know what's the short form, right? The true summary. Is it or isn't it? Okay. And So the long form is going to have a lot more details in it. You need to know them both. Okay? Here are all the things in the long form. You'll have this list. I'll give this to you so you'll know what the list is. But then, and we're going to do this for the example so you can see how each part of this gives us information that we want to know when we're drawing a conclusion. 95% confidence. There is evidence. That's what we're saying. There is evidence to prove this. And we don't care about the sample. We're asking, what is the population proportion of students? It's greater than that in the national survey. So yeah, we proved it. That's great. There are only two possible conclusions. Either we proved what we set out to prove, or there's no decision. As you go through the examples, you'll see this. It's important that you understand. Either we proved it, which is a good thing, or we cannot make a decision. Now there's another.
Okay, we're going to stop that before we get to the next part. Okay. Now, I've had this problem at various times in various classes. What we're going to do is we're going to take the Monday homework and we're going to put it on to Wednesday. Okay, so the homework, which is right now scheduled for Monday of next week, is going to be on Wednesday of next week. But also, the Wednesday homework is not going to go away. So whatever you're able to get done on this Monday homework before we have class on Monday will be helpful. Because on Wednesday, we're going to do this like with 4 more things, right? So you'll need to start this process. You'll need to take a look through these videos. You need to take a look at the homework, see what kinds of things you're expected to do, but we're not going to have it due on Monday, all right? It's going to be due on Wednesday. All right, we'll go from there.
And you tried to create a way to do a I was like, oh my god. Because at first you did like the one loop, and I was like, what is she doing? And I saw you tuck it in, and I was like, oh my god, she didn't get it. My new favorite way. Like otherwise, like when I do a messy con, it always just looks like ratty. And I'm like, oh, this is the only time I've done it. This one. Like in the summer, I brush my hair all I want, but it's soon and I start brushing it. I hold it messy. So I know I had to put it up in the floor, I guess I did. So that it's not messy.